All right, so we're going to be talking about conjugate fields now. We talked about this map or this thing, this mind or this way of thinking of quantum fields, where we start off with a Lagrangian, right? And from the Lagrangian, we can then get something called a conjugate momentum field. And then from the conjugate momentum field, we then apply the quantum, this is sort of what I defined as the quantum entry into the field, right? This is why we call them quantum field theories. This is the idea that we have a commutation relationship between the solution to our Lagrangian and this conjugate field, and then from there we are able to get our annihilation creation operators and their relationships to one another. Okay, so that's sort of what we had gone over in the previous video. From here on out, I also want to disclose that I'm going to start putting videos on Patreon, so if you want to see videos early, then you can go into my Patreon page and contribute. And yeah, that's where you'll see more and more of the videos come up before I post them on YouTube. Anyways, that is what I'm just going to keep that there. So this was our sort of way of thinking about quantum fields, where we start with some Lagrangian, right? So the Lagrangian is the statement that this is the field we're talking about. So this is sort of the field, and then this is the quantum part. This is what makes them quantum fields, right? So we're going to keep this in mind as we progress throughout the rest of this book. Again, the book is No Nonsense Quantum Field Theory by Jacob Schwittenberg. And yeah, so let's get into now the topic of today, which is conjugate fields, right? So conjugate fields, those are these things that we were talking about, right? So these guys right here, we have, in particular, this is called the conjugate momentum density field, and it's going to be an integral importance because we then use it in our quantum commutation relationship later on. So let's see exactly what this thing is, where it comes from, why we have it in the first place, right? So if we recall from quantum mechanics, we have momentum, right? Momentum is a generator of spatial translations. We talked about this earlier, right? So, and this generator is an operator, which looks like this, right? So it's the spatial derivative with it's complex with I, and it's made quantum with Planck's constant, okay? And then energy also is the same thing, right? So energy is a generator of temporal translations, right? So same form, different signs, right? The different signs tell you something about the relationship between momentum and energy. And this is just the time derivative, right? So we have spatial derivatives and time derivatives, and these tell us something about the momentum and the energy of the particle, the quantum particle that we're interested in. Okay, so that's just a recap from quantum mechanics. If we're to recap just a little bit more, putting this in sort of a table form, we have quantum mechanics, right? And it's associated Noether's theorem, right? So we've talked about Noether's theorem in the past, way early on, where Noether's theorem tells us that for every operation, there's some sort of symmetry, or not every operation, but for some conserved quantity, there's some sort of symmetry that's involved. The symmetry comes in the form of what these operators do to our states to render them invariant. And so from Noether's theorem, we see that again, this is a spatial translation, right? So x represents some spatial some point in space, and epsilon represents some small change in that space, in that spatial point. Similarly, energy here, energy is associated with a shift in temporal energies, or not temporal energies, but a shift in time, and whatever remains invariant within that shift in time is associated with our energy, right? So, and again, we have it summed up here. So in quantum mechanics, we have our spatial translations, and we have our temporal translations here for energy, right? So this is basically kind of the same thing that we were talking about right here, okay? And then just also as a quick recap, we talked about internal symmetries and space-time symmetries, right? So internal symmetries occur, they look like this, right? Space-time symmetries, I will add that we have X, we talked about this earlier. We have this relationship, which is pretty much the same thing as what we have this relationship here, which is pretty much the same thing that we have right here, with the addition that our space-time also changes, right? So X becomes X prime plus some change in X, right? So we talked about this also and what that led to. We're not going to go back into the details of that because we already talked about that, right? So that was classical mechanics. This is just sort of to jog our memory a little bit. Let's get into this conjugate field now. So what I want to do is I want to take this idea of this conjugate momentum, or this, I'm just going to call it a conjugate field for right now, right? So, and you'll see why. So this is the solution to our Lagrangian, right? So I'll just write here that this is our Lagrangian solution. And this here is our conjugate field. And this is also a field here, right? Because they're both functions of space and time. So they're fields over space and they're fields over time. And what we are going to say here is that the conjugate field is the spatial, or is the derivative with respect to phi, right here. We can see this is something we derived also, right, when we were talking about our Lagrangians. This is a quantity that is associated with something that we're going to call the conjugate field, right? So this is the solution. This here is the conjugate to our solution, right? And we want to know what the commutation relationship is between the field and its conjugate. And how do we do that? Well, remember, we think of the conjugate in this way, which is the derivative with respect to the field at some point, right? So I've highlighted, we want this at different points also, right? And I'll provide an image to see, to help us understand this a little bit more, or a little bit better. And if we remember the conjugate, or not the conjugate, but the commutation relationship is simply this, right? So we just swap the order of the field and the operation. So here's the field, and the operation is taking the derivative with respect to the field, with respect to the derivative of the field. That's what we're calling the conjugate field. And then this here is the same thing as this. We're just swapping the order, right? So now our field comes out on the right side here. And we have to operate on something, so we're operating on this arbitrary state. And let's see what happens. Okay, so we have this, so here's our field again, nothing's changed. Again, nothing's changed here. Nothing's changed really. Nothing's changed from this step to this step right here for this first term. However, for this second term, we have to use one of the rules in calculus that we've learned or that you probably hopefully have learned from a calculus class that you've taken, which is the product. I believe this is called the product rule, if I remember correctly. It's been a while since I've taken calculus. I can't remember the names, but anyways, we want to take the derivative of this with respect to this, and multiply it by this guy, which is right here, and then we do the same thing. We're taking the derivative of this and multiplying by this, so that's right here. Now, here's the thing. So this here, or this term here, is essentially the same as this term here, right? And this guy's negative, this guy's positive, right? So what happens is that this term cancels out with this term, right? So we get that the commutation relationship between the field and its conjugate. So again, the commutation relationship between the field and its conjugate, when we define the conjugate as being the derivative with respect to the fields here, and I believe these should be not here. Okay. Just complete the brackets. Right, and so what we get this down here. And this is really only true, again, when x, or not true, but this is 0 when x and y are equal, and not 0 when x and y are not equal. Right, so that's why we have this y here. And we're taking the derivative with respect to some state. And so this is what we get right here. So the commutation relationship between the field and its conjugate is a direct delta function. This is the claim. This is the quantum mechanical claim that is being infused into our field theory, right? So I'm going to recap here really quick, or not really recap, but we'll go over this again in some more detail. So we have the field, right? So I'm just going to say this is our field, and this is, I'll do a different color here. This is our conjugate field. Okay, and so maybe to be a little bit more complete, this is, actually no, I'll be fine like that. And that the relationship is right here. It's a direct delta function between the field and the conjugate field. And so as a little pictorial image here, we have, let's see, I will draw, here's my field. Okay, here's my field, and here is my conjugate field. And we're saying at some point x, at some point here's x, and at some point y, we have there's a relationship between these 2 points, right? As the field, if we're talking about the same point, then that relationship is dictated by this delta function right here, okay? So if we remember what the delta function is that if the 2 things are the same, then it goes to 0. If the 2 things are not the same, if I'm remembering this correctly, it's so what is this? The delta function of x and y is 0 or 1, right? And it depends on what x and y are, right? So it's 0 if x and y are the same, or not the same. I'm not gonna reach into the back of my mind here. That's something you could look up, but this is the quantum. I don't want to say something wrong here, but that's the quantum mechanical claim. Anyways, we have that relationship, and so this is a claim about the relationship between two fields, one in which we have the conjugate. So conjugate again, and the field itself, right? So this really comes from just one field, right? The one field that's the solution to our Lagrangian. From that field, we can calculate the conjugate field. And the only tool we actually need in this case is one field. We don't need two fields here. This is just because the conjugate field comes from the solution, right? So we can call this a solution also, the field solution, or the solution field, whatever you want. These names are not really that important. The idea is just a concept that we want to get across. Again, that's why I was blanking on the Dirac delta function. I didn't want to say something wrong. This, again, is something that you could easily look up. But anyways, we have, again, I'm going to reiterate this point, and we'll reiterate this point as we progress on through the series here, this idea that you just need one field, and from that one field, you have this relationship that you can get, which is that the field or the solution to the Lagrangian has a conjugate, and the relationship between those two is a Dirac delta function. Why? Again, this comes from this, all of this comes from this derivation that we went through. And this derivation, again, you could start from this point, right? You could start from this point, but going through this derivation, I think, is much more satisfying, and it gives us more of a foundation as to what quantum field theory is. Someone could just come in, you could read a book, and it could start at this point. A lot of books probably do start at this point. They say, this is what we're gonna call our quantum fields. This is how we're gonna characterize our quantum fields through this relationship. I think it's just much more satisfying to go through the derivation to get to this point. And this is something, the reason this is the quantum mechanical claim is that if you think about positions and momentum, if you reach back into your mind of quantum mechanics, there's this relationship between the two, which is the Heisenberg uncertainty principle. And this is essentially a reflection of that principle, right? You can't know one. If you know the momentum, you can only arbitrarily really understand the other, and vice versa, right? You can't know both to arbitrary precision simultaneously. And that's why that's how we get to this conclusion, right? That's why we call this the quantum mechanical claim, right? Because in quantum mechanics, this essentially is the Heisenberg uncertainty principle. And that's sort of the wrap up here. That's the take home message we want to get here, which is that the field, you have the field, right? So we started here with a field, and we got its conjugate field. And then from that, we use the Heisenberg uncertainty principle that you could easily derive. And then from there, we investigate all of quantum field theory, right? And so that is conjugate fields in a nutshell. Later on, we're going to start talking about more in detail the Klein-Gordon quantum field theory, and then we're going to go into the Dirac quantum field theory, and then we are going to continue into the Proca quantum field theory, and we're just going to keep on going until we're done with this book, right? I understand it's been a while since I posted some stuff. I'm getting back into the swing of things. If you like this kind of stuff, again, please visit my Patreon page and hit that subscribe button. Thanks.